Welcome to this explainer. For decades, the engineers who run our electrical grids have really had one primary nightmare that keeps them up at night. What happens if a giant power plant suddenly fails? But, as we're about to see, the rise of artificial intelligence and hyperscale computing is completely flipping that script. We're going to look at a recent massive anomaly that served as a huge wake-up call for the entire power industry.
On July 22, 2026, more than 3 gigawatts of electrical demand simply vanished in an instant. Just to put that into perspective, 3 gigawatts is roughly the amount of power it takes to run several major cities all at the exact same time. It's a completely astronomical amount of electricity. And it didn't just slowly power down over a few hours, right? It disappeared in the blink of an eye.
This catastrophic drop happened across the PJM interconnection grid. Now, stretching across multiple states in the eastern U.S., PJM's footprint is absolutely massive. So when those 3 gigawatts dropped off, it didn't just cause some tiny localized blip. No way. It created a major voltage and frequency disturbance that was felt across a remarkably wide geographic area. The entire interconnected system took the shockwave.
Okay, so let's dive into the central mystery of this explainer. What could possibly cause a massive chunk of the power grid's demand to just evaporate? We aren't talking about a giant power plant breaking down here. We're trying to figure out how the actual users of the power could completely disconnect from the grid simultaneously.
According to Reuters, it was basically a rapid, automated domino effect. It all started with a transmission line outage in Northern Virginia. And, that area is famous for being the data center capital of the world. When that line faulted, numerous massive data centers in the region immediately detected the disturbance. To protect themselves, they automatically disconnected from the main grid and transferred over to their own backup power. The result? Boom! More than 3 gigawatts of demand were instantly severed from the system. Grid operators then had to scramble for 10 incredibly tense minutes just to stabilize the network.
To understand why an event like this is so terrifying for grid operators, we have to talk about the danger of excess generation. Normally, a grid is delicately balanced. Supply absolutely must match demand every single second. When you lose that much load instantaneously, the grid is suddenly left with gigawatts of dangerous, leftover power. Actually, think of it like pedaling a bicycle as hard as you can and suddenly the chain just snaps off. Your pedals are going to spin totally out of control, right? On the grid, this causes electrical frequency to spike rapidly. This means an event that starts at the consumer level can actually propagate outward and potentially damage equipment across the whole system.
Industry experts are taking this seriously. Sam Malecki over at EdgeTune Power hit the nail on the head, calling this a massive wake-up call. Power systems have traditionally been designed with a heavy emphasis on what happens if we lose generation. But this Northern Virginia event proved that system stability is increasingly becoming a load-side problem as well. Our entire traditional perspective on grid design has to change because the very nature of what consumes our power is changing.
What we're doing right now is essentially forcing two entirely different engineering philosophies to interact on the exact same physical wires. The new, highly electronic loads of AI data centers, they don't behave anything like the traditional components the grid was originally built for. It's forcing us to completely rethink historical grid planning to accommodate this wild new reality.
The real reason the 3 gigawatt load disappeared so fast comes down to competing objectives. Look at it this way. The conventional power grid has one goal, which is to save the utility and protect the power system and its assets. But AI data centers, they have a totally different prime directive. Their goal is to save the data center and ensure continuous, uninterrupted computing at all costs. For a data center running critical AI models, any interruption is just unacceptable. So, the moment they sense grid instability, their programmed instinct is to abandon the grid immediately to save their own operations.
And to make matters worse, the speed at which these two sides operate creates a really dangerous engineering mismatch. Conventional grid protections and controls usually react in hundreds of milliseconds, or sometimes even full seconds. But modern data centers, equipped with lightning-fast inverters and uninterruptible power supplies, react in mere milliseconds. Literally, before the conventional grid even fully realizes there's a problem, the data centers have already slammed the door shut and taken their 3 gigawatts with them.
Because of this fundamental mismatch in both speed and objectives, developers are facing a tough new reality. They now must ensure that very specific grid requirements are perfectly reflected in the actual physical behavior of the data center equipment during a crisis. It's just not enough to hope a facility stays connected. Things like how a facility rides through a voltage drop, how it coordinates its protections, and how it sequences its reconnection, all of that has to be rigorously proven. So the massive takeaway from the 3 gigawatt mystery? Basic computer models are no longer enough to guarantee grid stability. Historically, engineers relied heavily on these basic mathematical models, like positive sequence studies. But man, the industry learned the hard way that the incredibly fast control interactions of these modern electronic loads simply cannot be captured with conventional math alone.
To prevent another massive 3-gigawatt drop, the industry has had to seriously upgrade its toolset. Around 2020, they shifted to electromagnetic transients, or EMT simulations. But EMT still only tells us how a software model behaves. We have to take it a huge step further into real-time simulation in what's known as hardware-in-the-loop validation.
Hardware-in-the-loop, or HIL, is an absolute game changer. Think of it like a highly advanced flight simulator, but for grid equipment. Instead of just running a software model, engineers take the actual physical controllers, the real firmware, and the exact logic that will be installed at the data center, and they trick it into thinking it's connected to a real grid. They then hit it with simulated lightning strikes or transmission outages to see exactly how it reacts, long before it is ever allowed to connect to the real public grid. We are already seeing the tech industry mandate this evolution. Major players aren't waiting around for regulators to catch up. For instance, Nvidia's self-qualification guidelines now explicitly require hardware test evidence for battery energy storage systems. They are demanding hard proof, whether through bench testing, factory tests, or HIL, of exactly how the equipment handles dynamic responses, how it buffers massive AI loads, and how it smoothly manages the transitions between the main grid and islanded backup power.
But here's the crucial point, and it's something Nvidia emphasizes as well. Passing individual equipment qualification does not automatically guarantee site-level stability. Just because one single battery controller passes a test doesn't mean that thousands of them, working alongside cooling systems and AI servers, won't accidentally trigger a massive shutoff when they all interact with each other during a real grid event.
That is exactly why the next critical step is system-level validation. Using real-time data center testbeds, engineers are integrating the actual manufacturer controllers from the batteries, the solar panels, the backup generators, and the AI loads themselves, wiring them all together into one massive simulation. They are evaluating the entire ecosystem interacting as one unit, just to ensure they don't fight each other and crash the local grid when a real emergency strikes. The July 2026 event in Northern Virginia proved, without a doubt, that our old assumptions are officially dead. The modern grid is no longer just responding to giant spinning turbines and conventional generators. Increasingly, the very survival of the grid depends on the instantaneous, millisecond behavior of gigawatts of power electronic loads. The consumers are now so massive and they move so fast that they can literally dictate the stability of the entire system. Which leaves us with one final, urgent question to think about. Artificial intelligence and hyperscale computing are expanding at an absolute breakneck speed, demanding larger and larger chunks of power. As these enormous AI data centers continue to plug in, will our grid validation testing and our physical hardware simulations evolve fast enough to keep the lights on for all of us? It is quite literally a race against time, and the stability of our entire future infrastructure depends on the answer.